Hello there, and welcome to the Sleepy Space Channel. Tonight, the strange and quietly unsettling interior of the most distant giant planet in our solar system, and the picture of what is happening deep beneath its calm blue exterior. Neptune is, on the outside, an unbroken sapphire sphere, 4 times wider than the Earth. On the inside, it is a crushing furnace at temperatures comparable to the surface of the Sun, wrapped in an ice mantle in which water is predicted to exist as both a solid and a liquid at the same time, and in which methane breaks apart under pressure to produce a slow, continuous rain of solid diamonds falling through hot fluid toward the rocky core. The energy released by all of this drives the most violent atmosphere among the 4 giants. Over the next 2 hours, we will gently walk through every layer of that interior, from the cloud tops down to the core. If you find these slow explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The place at the edge of the light. The farthest of the major planets in our solar system orbits the Sun at an average distance of roughly 4.5 billion kilometers. That is, in practical terms, 30 times the distance between the Sun and the Earth. From where you sit, the Sun is a wide, bright disk that warms a hand held into its light. From Neptune, the same Sun is a sharp, brilliant point, smaller than a coin held at arm, any's length, no longer a disk at all. Its light takes a little over 4 hours to make the crossing. Its warmth, by the time it reaches Neptune's cloud tops, is essentially symbolic. This is the calm establishing fact that the rest of the night will rest on. The most distant of the 4 giants sits in a region of permanent twilight, in the outer edge of the Sun's gravitational neighborhood, in a place where the energy budget of the inner solar system has been diluted by roughly a factor of 900. It is, by every superficial measurement, the quietest neighborhood in the planetary system. It is also, by direct measurement, the home of the most violently active atmosphere among any of the giant planets. That is the unsettling and oddly fascinating contradiction at the center of this video. By the end of the next 2 hours, the contradiction will rest gently, named and explained. For now, you can simply hold it in mind, the way you might hold a small unanswered question in the back of a long, quiet evening. Neptune is the 8th and outermost major planet around the Sun. It is roughly 4 times wider than the Earth, with an equatorial diameter of about 49,500 kilometers. Its volume could contain about 57 Earths. Its mass is roughly 17 times the Earth's. Its density is about 1.5 times that of water, somewhat heavier than Saturn, somewhat lighter than Earth. If there were a place to stand at the depth where the pressure equals 1 Earth atmosphere, the gravity would feel only slightly heavier than the gravity you know. The planet, in absolute terms, is enormous compared to the Earth. In the family of giant planets, it is the smallest. The orbit is long. 1 full circuit of the Sun takes about 165 Earth years. Neptune has completed only 1 full orbit since it was first identified by astronomers. The axial tilt is about 28 degrees, close to the Earth, 23, which means that Neptune has seasons of a familiar shape, each one stretched out across roughly 40 years. The rotation period is about 16 Earth hours, faster than the Earth, 24. The planet spins quickly enough to organize its cloud structure into broad bands aligned with its equator. The Sun, from Neptune's point of view, is faint. At the top of the Earth's atmosphere, the Sun delivers about 1,360 watts of energy per square meter. At Neptune's cloud tops, the same Sun delivers about 1.5 watts per square meter. That is about 900 times less, or less than 1,000% of what reaches the Earth. From Neptune, the Sun is still the brightest object in the sky by a wide margin. It still casts shadows. It is still, unmistakably, a star at the center of a planetary family. But it is a beacon, not a furnace. It carries almost no warmth. The composition of Neptune is part of what makes it strange. The planet is classified as an ice giant, a designation it shares only with Uranus, and that distinguishes it from the gas giants Jupiter and Saturn. The outer envelope is a hydrogen and helium atmosphere, about 80% hydrogen, about 19% helium, with a small but important fraction of methane, about 1.5%. That methane is the reason Neptune looks the way it does. Methane absorbs red light and reflects blue. When sunlight reaches Neptune's upper atmosphere, the red is taken in and the blue is sent back out into space. The result is the deep, almost gem-like sapphire color that telescopes have shown for decades. Below the hydrogen and helium envelope, the planet changes its character entirely. The bulk of Neptune's mass is concentrated in a thick, hot, dense mantle of compressed water, methane, and ammonia. The word ice in the term ice giant is misleading. At the pressures and temperatures of Neptune's interior, these substances are not the familiar frozen solids that you might find on the surface of a small moon. They are exotic, high-pressure phases of matter, in some regions superheated fluids, in some regions states of matter that have no everyday counterpart on the Earth's surface. Below the mantle, at the very center of the planet, sits a small, rocky and iron-rich core, perhaps 1 to 1.5 Earth masses, under pressures of several hundred gigapascals and temperatures of perhaps 5,000 degrees Celsius, comparable to the surface of the Sun. Neptune, in other words, is not a frozen world. The cold belongs to the outer atmosphere. The inside is a crushing, hot, dense reservoir of compressed volatiles, and at the very center, a small rocky furnace operating at temperatures that match the surface of the star, whose light barely reaches the planet, cloud tops. From Earth, Neptune is unimaginably difficult to observe in detail. At a distance of about 4.5 billion kilometers, its disk subtends an angle in the sky of about 2 arcseconds, which is roughly the size of a coin viewed from 3 kilometers away. Resolving any structure on that disk from the ground requires exceptional atmospheric conditions or advanced adaptive optics. For most of the modern history of astronomy, Neptune was known only as a small blue dot at the limits of what telescopes could resolve. Its orbital period, its approximate size, its mass, its atmospheric composition in broad terms, the presence of methane, the suggestion of clouds, the existence of moons, all of this was known. The detailed character of the planet was almost entirely a matter of inference. That inference was strongly biased toward calm. Everything about Neptune's position in the solar system suggested that its atmosphere should be the quietest of any planet. Almost no sunlight reaches it. The temperatures are brutally cold, with cloud tops near -214 degrees Celsius. The available energy to drive any sort of large-scale atmospheric motion seemed, by every reasonable accounting, vanishingly small. And in the nearest comparable case, Uranus, the prediction had already been confirmed. Uranus, when visited up close, looked nearly featureless, a pale blue-green disk with almost no visible cloud structure. The expectation was that Neptune, even farther out and even colder, would be quieter still. the expectation was wrong by a factor that borders on absurd. And the rest of this video is, in one way or another, the story of how that turned out to be true. Part 2. The gradient that should have held. To understand why the expectation about Neptune was so strong, it helps to walk slowly through the solar system from the inside out. The basic intuition is one that every human being already carries, even without being told. The closer you stand to a fire, the warmer you are. The farther you walk from it, the colder you feel. Heat radiates outward. Distance dilutes it. The relationship is mechanical and clean. Light from the sun obeys the same rule. Each step outward from the sun reduces the amount of energy that arrives per square meter by the square of the distance. Double the distance, the energy per square meter falls to a quarter. Triple it, the energy falls to a ninth. By the time you reach the outer giant planets, the energy per square meter has fallen by enormous factors. The whole architecture of the solar system, in terms of energy, is organized by this single principle. In the inner solar system, the rule manifests as scorching heat. Mercury, the closest planet to the Sun, receives about 7 times more solar energy per square meter than the Earth does. Its dayside surface reaches roughly 430 degrees Celsius, hot enough to melt lead. There is no atmosphere worth speaking of to moderate the swings. The night side cools to extreme cold within hours of sundown. Venus, the second planet, sits a little farther from the Sun than Mercury, but its thick carbon dioxide atmosphere traps so much of the solar energy that its surface is hotter than Mercury. The surface temperature of Venus is about 460 degrees Celsius, sustained across both day and night by the dense greenhouse blanket. This is not a contradiction of the distance rule. It is a demonstration that what an atmosphere does with the available energy can matter as much as how much energy arrives. The Earth, at roughly 150 million kilometers from the Sun, sits at the distance that allows liquid water on its surface. The solar energy at the top of the Earth, atmosphere, is about 1,360 watts per square meter. That is, in cosmic terms, an extraordinarily generous allocation. The Earth's weather, with all its storms and seasons, is driven almost entirely by this solar input. Warm air rises near the equator and sinks at the poles. Temperature gradients drive winds. Winds drive ocean currents. Ocean currents redistribute heat back into the atmosphere. The entire system is an enormous, beautifully complex heat engine fed by sunlight. Mars, the next planet outward, sits at about 1.5 times the Earth distance. The solar energy that reaches Mars is less than half of what reaches the Earth. The result, predictably, is a colder world. Average surface temperatures on Mars are about -60 degrees Celsius. The atmosphere is thin and dry. Weather exists on Mars in the form of dust storms and the slow seasonal movement of frosts, but it is muted compared to the Earth. Seas. The planet has the energy to drive some atmospheric activity, but the magnitudes are reduced. Beyond Mars lies the asteroid belt, and beyond the asteroid belt, the gas giants begin. Jupiter, the first of the giants, sits at about 5 times the Earth's distance from the Sun. The solar energy that reaches Jupiter is only about 4% of what reaches the Earth. By the simple distance rule, you would expect Jupiter, atmosphere, to be relatively calm. It is not. Jupiter has spectacular weather. The Great Red Spot, a vast storm wider than the Earth, has been observed for at least several centuries. The atmosphere is organized into broad, alternating bands of cloud, each with its own wind direction and chemistry. Lightning storms scatter across the cloud tops. The planet is meteorologically alive. There is a reason. Jupiter is enormous. Its mass is more than 300 times the Earth's. Its gravitational compression generates substantial internal heat. Jupiter radiates about 1 7/10 of the energy it absorbs from the Sun. The atmosphere has access not only to the modest solar input, but to an even larger internal energy source. Jupiter. Weather makes sense on a careful accounting. Big planet, lots of energy, spectacular weather. The story holds together. Saturn, the next planet outward, sits at about 10 times the Earth's distance. The solar energy that reaches Saturn is only about 1% of what reaches the Earth. Saturn is also smaller than Jupiter, with a mass of about 95 Earths. It is, however, still large enough and warm enough internally to drive a powerful atmosphere. Saturn radiates about 1 8/10 of what it absorbs from the Sun. It produces a peculiar persistent hexagonal jet stream at its north pole, an occasional planet-encircling great white spot storm roughly once per Saturnian year, and a subtle but real banded structure across its disk. Saturn, atmospheric violence, is episodic rather than constant. But when the violence arrives, it can be enormous. Uranus, the seventh planet, sits at roughly 20 times the Earth's distance. The solar energy that reaches Uranus is only about 1/4% of what reaches the Earth. Uranus is comparable in mass and composition to Neptune, with about 14.5 Earth masses. When the Voyager 2 spacecraft visited Uranus in the mid-1980s, it found a nearly featureless pale blue-green disk. The atmosphere had almost no visible cloud structure. A handful of faint cloud bands could be coaxed out of the images through careful processing, and a few small discrete features appeared near the South Pole, but compared to the rich tapestry of Jupiter, or even the subtle banding of Saturn, Uranus looked smooth, calm, and meteorologically quiet. The reason, as later measurements confirmed, is that Uranus has very little excess internal heat. Its energy balance ratio is about 1 600ths, which is essentially indistinguishable from thermal equilibrium with the Sun. Whatever internal heat Uranus might have once carried, it does not, in the modern era, drive a strong atmospheric engine. The planet is cold inside and out, and its weather is correspondingly muted. This is the gradient that scientists in the late 1980s were carrying in their heads as Voyager 2 approached Neptune. Mercury was scorched. Venus was suffocated. Earth had moderate weather, driven by moderate solar input. Mars was cold and largely still. Jupiter was massive and internally heated, and it produced tremendous weather. Saturn was similar, but slightly calmer. Uranus was far, cold, and meteorologically dead. The logical conclusion was almost irresistible. Neptune, even farther from the Sun, even colder, even more starved of external energy, should be the quietest of them all. The far edge of the solar system should be where atmospheric activity gave up. The prediction was reasonable. It was conservative. It was supported by the freshest observational data, the direct measurements that Voyager 2 had already taken at Uranus only 3 years earlier. It represented the best thinking of the best planetary scientists alive, and it was about to be inverted by the planet itself. Part 3. The single flyby that inverted the picture. On a late summer day, at the very end of the 1980s, a small spacecraft that had been flying for 12 years passed within about 5,000 kilometers of Neptune's cloud tops. It remains the only spacecraft that has ever been close to the planet. Its data took more than 4 hours to make the journey back to Earth at the speed of light, weakened by distance to a whisper that radio telescopes on multiple continents had to combine to catch. Nothing about the encounter was easy. Almost nothing about it went the way the planning had predicted. Voyager 2 had launched in the late 1970s, designed to exploit a rare planetary alignment that allows a single spacecraft, using gravitational slingshots, to visit Jupiter, Saturn, Uranus, and Neptune in sequence. The alignment occurs roughly once every 175 years. The spacecraft was the second of 2, both launched in the same season. Voyager 1 had been routed to make a closer look at Saturn, large moon Titan, and had been sent on a trajectory that bent it away from the outer giants. Voyager 2 carried the entire weight of the outer planet survey. By the time it reached Neptune, the spacecraft had already been transformed several times by its journey. Its primary radio receiver had failed mid-mission, and the backup had been kept alive by careful engineering. Its scan platform, the mechanical structure that pointed the cameras and instruments, had seized during the Saturn encounter and required cautious reprogramming to be coaxed back into service. It carried instruments that had been designed in the 1970s, calibrated against the planetary science of the time, and pressed into service for environments their designers had only imagined in outline. Its plutonium power supplies were slowly cooling. Its computer memory was sized in kilobytes. Almost everything it did at the edge of what 1970s engineering could sustain across interplanetary distances. It made closest approach in the late northern summer, in the southern hemisphere of Neptune, passing within about 5,000 kilometers of the cloud tops. That was closer than it had come to any other planet on its tour. The flyby lasted hours. Neptune rotates once every roughly 16 hours, which meant that the spacecraft would see roughly half of the planet in sharp detail and then continue outward forever. Every minute of imaging time had been allocated months in advance. Every camera angle had been calculated to maximize coverage. The team on the ground was working in shifts to keep up with the data stream as it arrived. The first images from the approach phase showed Neptune as a blue disk, as expected from the methane composition. But as the resolution sharpened over successive days, the disk began to fill with structure that had not been predicted at all. Bright streaks of cloud appeared near the equator. Dark oval shapes resolved out of the blue background in the southern hemisphere. Bands of cloud formed at characteristic latitudes. Shadows, the first ever resolved on the cloud structure of a planet other than the Earth, were cast by high methane ice clouds onto deeper layers below. By the time the closest approach images arrived in late August, the team understood that every prediction about Neptune, quiescence, had been wrong. The planet, viewed close up, was a place of full atmospheric fury. The most immediately striking feature was a massive dark oval in the southern hemisphere. It measured roughly 13,000 kilometers long and 6,600 wide. That is, approximately the size of the Earth. The team named it the Great Dark Spot, in deliberate echo of Jupiter's Great Red Spot. The comparison was natural. Here was a storm system, on the most distant of the giants, that rivaled the most famous atmospheric feature on the largest. It was an anticyclonic vortex, rotating in the direction opposite to a low-pressure cyclone in that hemisphere. It drifted westward through the atmosphere at about 300 meters per second relative to the surrounding flow. Its shape oscillated rhythmically with a period of about 8 Earth days, stretching and compressing as it interacted with the surrounding wind field. It was not the only dark feature. A second smaller dark spot was identified farther south, informally called Dark Spot 2. Between the two storms, an extraordinarily fast-moving bright cloud feature was tracked as it raced around the planet at speeds that completed a full circuit every roughly 16 hours. The team gave it the playful nickname, the Scooter, in reference to its speed relative to the surrounding atmospheric features. Bright methane ice clouds formed in companion structures along the edges of the Great Vortex, casting shadows that confirmed they sat high above the deeper blue atmosphere. But the visual structure was only the most immediately striking part of the discovery. The wind measurements that came in over the following days were what truly broke the prediction. The way wind speed is measured on a giant planet is to track the apparent motion of cloud features over time and then compare that motion to the planet, underlying rotation. Neptune's underlying rotation rate had been deduced from the timing of radio emissions generated by its magnetic field, which gave the team a fixed reference frame. By tracking specific cloud features over hours and days against that reference, the wind speeds at each latitude could be calculated. What the data revealed was something that no one on the team had been prepared for. Near the equator, Neptune's atmosphere was moving in a powerful retrograde jet stream. That is, it was blowing in the direction opposite to the planet, rotation, westward across the disk, at sustained speeds of about 1,400 kilometers per hour. That works out to roughly 900 miles per hour, planet-wide, continuously. The direction itself was unusual. On Jupiter and Saturn, the equatorial winds blow prograde. With the rotation in the same direction, the planet turns. Neptune reverses the pattern. Its equator pushes westward against the planet, eastward rotation. At higher latitudes, the wind direction shifted back to prograde and became even faster. Near the latitudes where the Great Dark Spot lived, the winds approached 2,100 kilometers per hour. That works out to roughly 1,300 miles per hour. These were not gusts. They were not local extremes. They were sustained planet-girdling jet streams of an intensity that exceeded anything that had ever been measured on any other planet. To give those numbers a comparison that the Earth allows, the most powerful sustained tropical cyclone winds ever measured on the Earth have peaked at about 215 miles per hour. That is the ceiling of what the solar-driven, ocean-fed atmospheric machinery of the Earth has ever produced in the modern era. Neptune's sustained winds are roughly 6 times faster than that, planet-wide, continuously, without any nearby star to supply the energy. The implication of this measurement is not subtle. The energy budget at Neptune's distance is roughly 900 times smaller per square meter than the energy budget at the Earth's, and yet the wind speeds are roughly 6 times larger. The ratio of wind speed to available solar energy is grotesquely out of proportion to anything that the inner solar system would predict. Some other source of energy has to be supplying the atmosphere. The sun, at that distance, is a spectator. Something else is driving the engine. The wind structure across the planet, even apart from its raw speed, was organized in a way that revealed the depth of the system. Like Jupiter and Saturn, Neptune's atmosphere is divided into alternating latitudinal bands, where the wind blows in different directions. The equatorial zone carries the powerful retrograde jet. The mid-latitudes carry the even faster prograde jets. Toward the poles, the wind structure reorganizes into smaller features. This banded architecture is a signature of deep, persistent, organized flow. It is not the kind of pattern that random turbulence would produce. The winds are not gusts or squalls. They are permanent features of the planet's atmospheric circulation, maintained continuously across decades despite the negligible solar heating available to sustain them. The number of bands on Neptune is fewer than on Jupiter, and the bands themselves are broader. Jupiter has dozens of narrow alternating jets visible in its cloud structure. Saturn has fewer, but still multiple distinct ones. Neptune has a simpler pattern, with fewer, broader latitudinal zones and fewer distinct jet streams. The simplicity is, at first glance, a sign of less activity, but the opposite is the case. The fewer broader jets concentrate the atmospheric energy into larger-scale flows, which is part of why the velocities are so extraordinary. The atmosphere is not dissipating its energy across many small features. It is channeling it into a small number of enormous rivers of wind that circle the entire planet. By the time Voyager 2 left the Neptunian system, the conventional understanding of how the outer solar system worked had been put under structural strain. The smallest of the giants, the coldest of the giants, the farthest of the giants, the one with the least solar energy by a wide margin. And yet, on every measurement that mattered, the one with the most violent atmosphere among them, something fundamental about the relationship between distance, energy, and atmospheric activity had been incomplete, and the spacecraft had just spent a few hours making that incompleteness impossible to ignore. Part 4. Storms that form, drift, reverse, and vanish. Neptune does not merely have weather. It has a storm system that operates on a tempo unlike anything else in the solar system. The dark vortices that the Voyager spacecraft saw at the planet are not simple eddies in a slow current. They are large, organized, anticyclonic systems that form deep in the atmosphere, persist for a few Earth years, drift across many latitudes, and then either fade or actively break apart. Watching the storms across decades is something like watching a tide come in and out across an evening that is too slow to perceive in real time, and yet far faster than the long seasons of the planet itself. The Great Dark Spot, the largest of the storms seen by Voyager, was an anticyclonic vortex roughly the size of the Earth, embedded in the deeper atmosphere of Neptune, southern hemisphere. It rotated counterclockwise, drifted westward through the wind field, and oscillated in shape over a period of about 8 Earth days. Bright methane ice clouds formed in companion structures along its edges, where rising air cooled enough to allow methane gas to condense into ice crystals at altitude. The dark color of the spot itself is thought to arise from downwelling air, clearing the upper methane haze, exposing a deeper, darker atmospheric layer beneath. More recent spectroscopic work suggests that the dark color may also involve a darkening of the aerosol particles within the vortex itself, not only a clearing of the haze above them. The dark spot looked, in its broad strokes, like a younger cousin of Jupiter's great red spot. Both were anticyclonic. Both were comparable in size relative to their host planet. Both occupied a similar latitude. The Great Red Spot on Jupiter has been stable for at least several centuries, possibly longer, and may be one of the most persistent atmospheric features in the entire solar system. By analogy, the team expected that the Great Dark Spot might be a similarly long-lived structure, perhaps observable for decades or centuries. That assumption lasted exactly 5 years. When the Hubble Space Telescope turned its optics toward Neptune in the mid-1990s, the Great Dark Spot was gone. Not faded. Not diminished. Gone. The smaller dark spot had also vanished. In place of the southern features, Hubble found a new dark spot in the northern hemisphere, as though the planet had quietly dissolved one storm and produced another in a different location. This pattern has continued in the long observational record that has accumulated since. multiple dark vortices have been observed across the decades, each appearing at different latitudes, in different hemispheres, persisting for a few Earth years, and then fading. Based on the cumulative observational record, astronomers now estimate that Neptune hosts a major dark vortex roughly half the time. The planet cycles through periods of spotted and unspotted appearance with a cadence that suggests continuous internal storm generation, balanced against dissipation processes that destroy the vortices after relatively short lifetimes. This is not how giant planet storms are supposed to work, by the example of Jupiter. The Great Red Spot is a permanent feature. The dark spots are temporary ones. Some mechanism on Neptune that does not operate on Jupiter is generating and destroying storms on timescales of years. The atmosphere is not simply violent. It is unstable on a rhythm that is fast for a planet of Neptune size, and slow for any structure that a human being could watch in real time. One particular episode has come closer than any other to letting astronomers watch the death of a storm directly. In the late 2010s, the Hubble Space Telescope detected a new dark vortex in Neptune's northern hemisphere. It was roughly 7,400 kilometers across. Over the following years, the storm was tracked as it drifted slowly southward toward the equator. Atmospheric models predicted that, at the latitudes it was approaching, the wind shear between the retrograde equatorial jet and the prograde mid-latitude flows would tear the storm apart. The storm appeared to be heading directly toward its destruction. Then it did something no model had predicted. It reversed direction. It stopped its southward drift and began moving back toward higher latitudes in the north. At the same time, a smaller dark feature appeared near it, alongside the main vortex. The interpretation that emerged was that the smaller feature was a fragment of the main storm, an internal piece that had broken off as the main vortex experienced a disruption process. If confirmed, this would have been the first direct observation of the active disruption of a Neptunian dark spot, captured in something close to real time. For decades, the only data scientists had was the appearance and disappearance itself, as recorded in observations months apart. The mechanism by which a storm dies, between one observation and the next, had remained invisible. The 2018 storm offered a glimpse. A storm caught in the act, both reversing direction and shedding a fragment, suggested that at least some dark spots undergo active fragmentation, rather than gentle dissolution. If that is the typical end of a Neptunian storm, then the energy released during fragmentation might in some cases feed back into the surrounding atmosphere and potentially help to seed the formation of new storms elsewhere. Neptune, atmospheric circulation, may operate as a self-sustaining cycle, in which the death of one storm contributes some of the conditions that allow the next storm to form. None of this is certain. It is, instead, the kind of structural understanding that decades of patient observation can suggest without quite proving. There is also the question of what these storms physically are. The leading interpretation has been that the dark spots are anticyclonic vortices in the deeper atmosphere, where downwelling air clears away the upper methane haze and reveals darker layers beneath. The bright companion clouds that accompany the dark spots are thought to be high-altitude methane ice, forming where air is forced upward along the periphery of the vortex and cools enough to allow methane to condense. That picture fits the Voyager data. It fits much of the Hubble data, but it leaves out some of the recent ground-based spectroscopy. In the early 2020s, using the multi-unit spectroscopic Explorer instrument on the European Southern Observatory's Very Large Telescope in Chile, astronomers detected a Neptunian dark spot from the ground for the first time in history. Every previous dark spot detection had required either Voyager up close or the Hubble Space Telescope above the distorting effects of the Earth's atmosphere. The ground-based detection was significant on its own, as a technical achievement. What made it scientifically important was the spectroscopic data that accompanied it. The spectrum showed that the dark appearance of the storm was not simply a window through to deeper layers. It was, at least in part, a darkening of the aerosol particles within the storm itself. The vortex was altering the chemistry of the particles inside it. A bright companion feature, observed alongside the dark spot, turned out to be a deeper cloud layer at a different altitude than the typical methane ice clouds, with a distinct vertical structure that imaging cameras alone could not resolve. Each new observation adds complexity rather than clarity. Neptune's storms yield their secrets slowly. They appear in different hemispheres. They drift across many degrees of latitude. They oscillate. They reverse course. They sometimes fragment. They produce companion clouds that occupy different layers of the atmosphere. They sometimes alter the chemistry of the particles inside them. They are organized, persistent on the timescale of a few years, and then they are gone, and a new one appears somewhere else. That cadence, by itself, is one of the strangest things about Neptune. Jupiter's Great Red Spot has been there for the entire history of telescopic astronomy. Saturn's great storms are episodic but predictable, returning once per Saturnian year of about 30 Earth years. Neptune's storms come and go on a rhythm of 2 to 5 years, half the time leaving the planet visibly spotted, half the time leaving it visibly bare. The atmosphere is, in some sense, breathing its storms in and out across that rhythm. Each cycle is generated by the internal engine, sustained for a while by the slow-moving wind field, and then quietly dissolved or torn apart by the same wind field that had previously held it together. The planet does this without effort, without external trigger, without prompting. It has presumably been doing it for as long as the engine inside has been running, which is to say, for as long as the planet has existed. Part 5. The clouds that come and go with the Sun. Beyond the dark vortex storms, Neptune's atmosphere has another form of variability that is, in its own way, as striking. The mid-latitude cloud bands that have decorated Neptune's disk across the modern observational era can thin, vanish almost completely, and then reform on timescales of only a few Earth years. The rhythm of this disappearance and return turns out to be quietly tied to the 11-year activity cycle of the Sun. A world that receives almost none of the Sun's warmth nonetheless responds, faintly and visibly, to the Sun's shifting mood. For most of the long Hubble era, Neptune appeared as a deep blue disk decorated with bright methane ice cloud bands at mid-latitudes. The bands moved, shifted intensity, formed and dissolved on small scales. But as a class of feature, they were almost always present. Side-by-side images of Neptune taken in different years showed familiar architecture. A bright band here, a bright spot there, a persistent cap of cloud activity over the South Pole. Beginning toward the end of the 2010s, the mid-latitude clouds began to thin. Within a couple of years, they had almost completely disappeared. By the early 2020s, Neptune appeared nearly bare. The familiar bright bands were gone. The disk was a smooth, even, deep blue sphere. Only a faint residual cap of cloud over the South Pole remained. The planet looked stripped down to its underlying color, like a painting whose foreground figures had been quietly erased and only the background sky left behind. The change was documented across a long stretch of observational record by combining decades of images from the Hubble Space Telescope the Keck Observatory, and the Lick Observatory. The longer record, when viewed as a whole, showed a clear and repeating pattern. Neptune's cloud abundance rises and falls in step with the Sun's 11-year activity cycle, but with a lag of about 2 Earth years between the Sun's peak and Neptune's peak. When the Sun's ultraviolet output increases, Neptune's cloud cover grows brighter. But 2 years later, when the Sun's ultraviolet output declines, Neptune's clouds fade, again about 2 years later. The correlation appears across 2.5 complete solar cycles. It is robust, repeatable, and quietly astonishing. The astonishing part is not that the Sun influences Neptune's atmosphere. The Sun, after all, is the only meaningful energy source from outside that the planet has. The astonishing part is that an energy budget so faint can still be tracked in the visible appearance of a world 4.5 billion kilometers away. Most of the energy Neptune uses to drive its weather comes from inside. The internal engine is large compared to the trickle of solar input. And yet the visible clouds at the very top of the atmosphere respond to the small remaining influence of the Sun on a timescale of only a few years. The mechanism, in outline, runs like this. Ultraviolet photons from the Sun, even at Neptune's distance, can reach the upper atmosphere. There, they break apart methane molecules. The fragments recombine into more complex hydrocarbons. Some of those hydrocarbons, like ethane and acetylene, slowly settle downward through the atmosphere over months and years. When they reach altitudes where the temperatures and pressures permit condensation, they serve as nucleation seeds, the microscopic centers around which methane ice clouds can form. When the Sun's ultraviolet output is high, more methane gets broken apart, more hydrocarbons get made, more seeds settle down through the atmosphere, and more clouds form. When the Sun's ultraviolet output is low, less methane is broken apart, fewer seeds form, and the clouds eventually fade as the existing population of seeds runs down. The 2-year lag between solar activity and Neptunian cloud activity is roughly the time required for the chemistry to travel through the upper atmosphere from where the ultraviolet light is absorbed to where the clouds can form. The recent low point in Neptune's cloud activity in the early 2020s was the most extreme cloud minimum ever recorded for the planet. The disk appeared genuinely different from the way it had appeared during most of the Hubble era. And yet, beneath that smooth blue exterior, the underlying wind structure persisted unchanged. The jets continued racing around the planet at their extraordinary speeds. The internal heat continued rising through the atmosphere. The dark vortices continued forming and dissolving in their slow rhythm. The clouds are the visible traces of deeper processes, not the processes themselves. Their disappearance hid the surface expression of the violence. It did not stop the violence. In recent observations, the clouds have begun to return, consistent with the rising phase of the most recent solar cycle. Neptune is dressing itself again, reassembling the bright structures that telescopes had tracked for decades. The variability is, in its own way, a quiet reassurance. The planet is not stuck. It cycles. It breathes. It changes. The change is faint by the standards of an inner planet that has weather every day, but it is unmistakable on the long timescale of patient observation. There is something both calming and slightly disquieting about this responsiveness. Calming, because it shows that even the most distant and apparently isolated body in the planetary system is not entirely cut off. The Sun, even reduced to a sharp point of light, still reaches Neptune, and Neptune still responds. slightly disquieting, because it suggests that everything on this world, every visible mark, every faint band, every cap of cloud, is part of a slow conversation with a star so faint that you could not feel it on your skin. The conversation has been going on for billions of years. We have only been listening, with telescopes able to detect the conversation, for a few decades. The variability we have caught is, almost certainly, only a fraction of the variability that has been there the whole time. Part 6. The engine inside the planet. This is the part of the night that holds the central physics, and it is worth taking slowly. The sun cannot be powering Neptune's violence. The arithmetic does not allow it. The energy that reaches Neptune from the sun is small enough, by a factor of 900 relative to the Earth, that even a perfectly efficient atmosphere could not produce the observed wind speeds from solar input alone. The answer lies inside the planet itself, in an internal heat source that has been running quietly for 4.5 billion years, and that, by the cleanest comparison available in the solar system, distinguishes Neptune from its near-twin Uranus in a way that no one has yet fully explained. Consider the energy at hand. The Earth, at the top of its atmosphere, receives about 1,360 watts per square meter from the sun. The Earth uses that energy budget to drive every weather system it has, including its most extreme tropical cyclones, which top out at sustained wind speeds of about 215 miles per hour. That is the ceiling of what solar-driven, ocean-fed atmospheric machinery has been able to produce on a planet richly supplied with solar input. Neptune, at the top of its atmosphere, receives about 1.5 watts per square meter from the sun. That is about 900 times less than the Earth. And Neptune sustains winds of about 1,300 miles per hour, planet-wide, as a permanent feature. The ratio of wind speed to available solar energy is, in plain terms, grotesque. Roughly 6 times the wind speed, on roughly 1/900th of the energy. There is no atmospheric mechanism that can convert sunlight into kinetic energy with anything close to the efficiency that this ratio would require. The sun, at Neptune's distance, simply cannot be the answer. Something else has to be supplying the energy that drives the atmosphere. When Voyager 2 measured Neptune's thermal emission during its flyby, it confirmed what the wind speeds had already implied. Every object warmer than absolute zero radiates infrared energy, and the total amount radiated depends on the object, temperature, and surface area. By measuring how much infrared energy Neptune was emitting across the full range of wavelengths, scientists could calculate the planet's total thermal output and compare it to the total solar energy that the planet was absorbing. The result was clear. Neptune radiates about 2 6/10 times more energy than it absorbs from the sun. The difference is the planet's own internal heat flux, leaking outward into space. In absolute terms, the internal flux is modest, perhaps a few tenths of a watt per square meter, but compared to the trickle of solar input at Neptune's distance, it is substantial. The sun, in total, contributes less than 40% of the energy that flows through Neptune's atmosphere. More than 60% of that energy comes from inside the planet. This single measurement reframes the entire question. The winds, the storms, the dark spots, the cloud variability, the auroras, the upper atmospheric temperature changes, the long-term meteorological character of the planet, all of it is being driven by an engine that lives inside Neptune itself. The sun is not the engine. The sun is the calibration. The internal source is what is doing the work. The natural next question is where that internal heat actually comes from. The most straightforward answer the one that applies in some form to all 4 giant planets, is that some of the heat is residual from the planet. See formation. When a giant planet forms by accretion in a protoplanetary disk, the collapse of gas and dust into the planet releases enormous amounts of gravitational potential energy. Some of that energy radiates away during formation. Some of it is trapped in the planet, is interior, stored as thermal energy in the compressed materials. Over billions of years, the trapped heat slowly conducts and convects outward, eventually reaching the atmosphere and radiating into space. This process is sometimes called Kelvin-Helmholtz contraction. It accounts for much of the internal heat observed on Jupiter and Saturn. Those planets are massive enough that the energy they trapped at formation was very large, and they continue to release it at significant rates. The numbers fit. Jupiter, energy balance ratio of about 1 7/10, and Saturn, S, of about 1 8/10, are consistent with the standard models of planetary cooling for bodies of those masses and ages. Neptune, S energy balance ratio of about 2 6/10, is, in one sense, comfortably within the framework. The planet formed from an enormous amount of material collapsing under gravity. It trapped a substantial reservoir of thermal energy. It continues to release that energy slowly over geological time. The numbers are consistent, in broad strokes, with what you would expect for a body of Neptune's mass and age. Where the picture becomes uncomfortable is the comparison with Uranus. Uranus and Neptune are siblings. Uranus has a mass of about 14.5 Earths. Neptune has a mass of about 17 Earths. They have similar diameters. They have similar bulk compositions, dominated by exotic ices over a small rocky core, wrapped in a thin hydrogen-helium atmosphere. By every obvious metric, the 2 planets should have similar internal heat budgets. They should radiate similar amounts of excess energy. They should drive similar weather. They do not. Uranus radiates almost no excess heat. Its energy balance ratio is about 1 6/100, which is essentially indistinguishable from thermal equilibrium with the Sun. Whatever internal heat Uranus might once have carried, it does not, in the modern era, reach the atmosphere in any significant amount. The result is the bland, featureless, meteorologically quiet planet that Voyager 2 found in the mid-1980s. There are 2 broad possibilities for what makes Uranus different. The first is that Uranus has actually lost more of its internal heat than Neptune has, perhaps as a consequence of an ancient catastrophic event in its history. The most popular candidate is the same event that is thought to be responsible for Uranus: E's peculiar 98-degree axial tilt, an enormous collision early in the planet history that may have knocked the planet onto its side. The same collision, in this picture, also disrupted the planet's internal structure in a way that allowed the original formation heat to escape more rapidly than it otherwise would have. The second possibility, which is gaining popularity, is that Uranus is still hot inside, but the heat cannot reach the atmosphere. In this picture, the planet has a stable thermal stratification, a layer in the deep interior that blocks efficient convection. Heat from below is trapped beneath that layer and cannot rise through it. The result is an outer planet that radiates almost none of its internal energy, even though the energy is, in some sense, still there in storage. The atmosphere starves of internal heat because the path from the engine to the atmosphere is closed. Neptune, in this picture, avoided whatever happened to Uranus. It retained its conventional axial tilt of about 28 degrees, which is close to the Earth/X. It retained efficient convection from the deep interior to the cloud tops. The heat from formation rises freely through the ice mantle and into the atmosphere, where it drives the wind structure and the storms. The difference between the two planets is not necessarily a difference in how much heat each one has. It may be a difference in whether the heat can escape. There are other candidate explanations as well. Differences in interior composition could change thermal conductivity. Differences in ongoing gravitational settling could provide a continuing source of heat in one planet and not the other. There is also the possibility, explored in some models, that Neptune is still actively differentiating, with denser materials slowly sinking toward the core and releasing gravitational potential energy on the way down. If this is occurring, then Neptune's internal heat is not solely a relic of formation. Some of it is being generated in real time by the ongoing slow rearrangement of the planet interior. Among the candidate processes is one that planetary scientists have been studying with some affection. At the pressures and temperatures of Neptune's deep mantle, methane dissociates. The carbon atoms are squeezed out of their bonds with hydrogen, and the freed carbon is compressed into diamond crystals. The hydrogen, lighter, rises upward through the surrounding fluid. The diamonds, denser, sink downward through the same fluid. Over very long time scales, the result is something close to a slow, continuous rain of solid diamonds falling through the deep ice mantle toward the rocky core. As the diamonds sink, they convert gravitational potential energy into heat. If diamond rain is occurring inside Neptune, it provides a mechanism for continuous internal energy generation, supplementing the original heat from formation. The honest summary is that no one yet knows exactly which combination of processes is responsible for Neptune's excess heat. Several mechanisms are plausible. Several mechanisms may be operating together. What is certain is that the heat is real. The wind speeds confirm it. The thermal infrared measurements confirm it. The storms confirm it. The cloud variability confirms it. The auroras and the upper atmospheric heating confirm it. The planet is running on its own engine, deep inside, and that engine has been running for 4.5 billion years without any sign of slowing. The Uranus-Neptune comparison is, in some sense, the cleanest experiment the solar system has run on the question of what powers giant planet weather. Two planets, nearly identical in mass and composition, with dramatically different internal energy budgets and correspondingly dramatically different atmospheric behavior. One is calm. One is the most violently active giant in the family. The atmospheres are responding, in real time, to the energy that reaches them from below. Where the path is closed, the atmosphere falls quiet. Where the path is open, the atmosphere runs at full speed. Part 7. Why a modest engine builds extreme wind. There is still a missing step in the explanation. Granted that Neptune has an internal heat source, granted that the heat flux is real, the absolute magnitude of that flux is small. We are talking about fractions of a watt per square meter, set against an atmosphere that produces sustained wind speeds of more than 1,300 miles per hour. By any naive accounting, this trickle of energy should produce gentle breezes at most. The fact that it produces the most extreme winds in the solar system requires a separate explanation, which lies in how the energy is distributed and how the atmosphere holds on to what it has been given. Three factors, working together, account for the inversion. The first is that Neptune has no solid surface. The second is that the active wind layer at the top of Neptune's atmosphere is extraordinarily thin. The third is that the extreme cold of the upper atmosphere reduces internal friction nearly to zero. Together, These three factors produce something close to a frictionless flywheel, an atmosphere that converts a modest energy input into a permanent, planet-wide kinetic flow with a retention efficiency that no warmer or rougher world can match. The first factor is the absence of a solid surface. On the Earth, atmospheric winds lose enormous amounts of kinetic energy to friction with the ground. Air moving across oceans is slowed by waves and spray. Air moving across forests is slowed by branches and leaves. Air moving across cities is slowed by buildings. Air moving across mountains is forced upward, around, and over the topography, dissipating energy at every turn. Hurricanes weaken rapidly when they make landfall, precisely because the rough terrain disrupts their circulation and drains their energy. Earth's atmosphere is a leaky system in this regard, because every wind it produces is in constant contact with friction-bearing surfaces. Neptune has no solid surface anywhere near its visible atmosphere. The hydrogen-helium envelope transitions gradually into denser layers as depth increases, but there is no abrupt boundary, no rocky crust, no ocean floor against which the wind can drag. The winds blow unimpeded across the entire planet, circulating around the equator and the higher latitudes without ever encountering an obstacle that might slow them. Kinetic energy that enters the atmosphere as wind stays as wind. There is no surface friction to convert it back into heat. The second factor is the shallowness of the active wind layer. Research into Neptune, atmospheric dynamics, primarily through careful tracking of how the planet, gravitational field, responds to atmospheric mass distribution, has revealed that the fast-moving wind layer is confined to approximately the outermost 0.2% of Neptune's mass. In absolute terms, that corresponds to a layer perhaps 600 to 1,000 kilometers deep at most. Below this layer, the atmosphere transitions into the dense, slow-moving interior, where the standard rules of atmospheric circulation give way to the rules of dense compressed fluids. This shallowness has a counterintuitive consequence for how fast winds can become. A given amount of thermal energy rising from the interior does not need to accelerate the entire atmosphere to produce fast winds. It only needs to accelerate the thin shell of relatively low-density gas at the very top. The mass of this shell is tiny compared to the total mass of Neptune. Moving a small mass of gas very quickly requires far less energy than moving a large mass of gas moderately quickly. Neptune's atmosphere reaches extraordinary velocities precisely because the moving layer is so thin. The internal heat flux, modest in absolute terms, is concentrated into accelerating a comparatively small mass of atmospheric gas, and the result is extraordinary speed. The third factor, and the most counterintuitive of all, is that the extreme cold of Neptune, its upper atmosphere, helps. At cloud-top temperatures near -214 degrees Celsius, the atmospheric gases have very low thermal energy, which translates into very low viscosity. Viscosity, in a fluid, is the internal friction between adjacent layers, the resistance that one moving layer exerts on the layers next to it. In a warm, dense atmosphere, viscosity acts as a brake on wind speed. It converts kinetic energy into heat through internal molecular friction. The faster a parcel of air moves, the more the surrounding parcels resist its motion, and the more kinetic energy is bled off as heat. In Neptune's frigid atmosphere, this internal friction is dramatically reduced. The cold gas offers almost no resistance to being moved. Once a parcel of atmosphere acquires velocity, it retains that velocity with minimal loss. The winds, having been accelerated by the rising internal heat, simply keep going. Combine the three factors and the picture comes together. Energy from Neptune is interior enters the base of the wind layer as thermal convection. The convection accelerates the thin shell of upper atmosphere into motion. There is no surface to slow that motion. There is almost no viscosity to absorb that motion. There is almost no efficient radiative path that allows the kinetic energy to leak away. The wind, once started, persists. New energy from below keeps adding to the flow. Old energy stays where it has been put. The atmosphere accumulates velocity over time, like a flywheel in a vacuum, until it reaches the extraordinary speeds observed. The same logic, in reverse, explains why Uranus is so quiet. Uranus has the same advantages, in principle, as Neptune. It has no solid surface. Its upper atmosphere is also extraordinarily cold, with viscosity correspondingly low. Its wind layer is presumably shallow as well. The flywheel architecture is, in some sense, already there. What Uranus lacks is the energy input from below. The internal heat flux is too small to drive significant atmospheric flow. The flywheel exists, but the engine is essentially turned off. The result is a calm planet whose architecture, on paper, ought to allow violence, but does not have the energy to express it. There is a useful way to hold the comparison. The Earth, atmosphere, absorbs about 20 times more total energy than Neptune, atmosphere, does, from all sources combined. The Earth uses that enormous budget to produce maximum sustained winds of about 215 miles per hour in its most extreme tropical cyclones, and only for a few days at a time in localized regions. Neptune, with a total atmospheric energy budget, roughly a 20th the size of the Earth, produces sustained winds exceeding 1,300 miles per hour as a permanent planet-wide feature. The ratio of wind speed to total available energy on Neptune exceeds the Earth, to ratio by a factor that seems, at first glance, to violate intuition about how atmospheric physics should work. The resolution is that wind speed is not a simple function of total energy input. It is a function of how the energy is distributed and how efficiently it is retained. Earth, atmosphere, is leaky. Most of the solar energy that enters it is lost to other processes before it can become wind, heating the ground and the oceans, driving evaporation, driving precipitation, radiating away from the atmosphere into space at infrared wavelengths. Only a small fraction of the incoming energy ever becomes kinetic flow, and even that small fraction is then ground down by surface friction. Neptune, atmosphere, is the opposite. It is the closest thing to a closed system that planetary science has observed at this scale. The energy entering the base of the wind layer has almost nowhere to go except into accelerating the gas. There is no surface to dissipate kinetic energy. There is minimal turbulent dissipation because the extreme cold suppresses the small-scale instabilities that generate turbulence in warmer atmospheres. There is little radiative loss because the atmosphere is largely transparent at the wavelengths where the thermal radiation of the wind layer would carry energy away. The result is an atmosphere that retains the kinetic energy it has been given for very long times, accumulating motion over years and decades, and producing winds that no warmer planet can match. There is something almost gentle in that description when you hold it at the right register. Neptune is not an atmosphere that fights itself into high speeds. It is an atmosphere that accepts a small input quietly, holds onto it almost without loss, and lets it ride for as long as the engine inside keeps providing more. The winds that you would feel, if you could somehow stand inside that flow at the cloud tops, would not be a battering chaos. They would be a steady, smooth, planet-wide river of frigid gas, moving with almost no internal disturbance, faster than any sound could travel through the thin, cold air, faster than any earthbound storm has ever moved, faster than the imagination ordinarily allows for atmospheric motion. The speed is real. The violence is real. The driver, by every measurement available, is patient and modest and quietly persistent. Part 8. The tilted field and the mid-latitude auroras. Neptune, magnetic field, is one of the strangest in the solar system, and it shapes how external energy enters the planet, atmosphere. Most of the planets in our family carry magnetic fields whose axes are reasonably well aligned with their rotational axes. The Earth's magnetic field tilts by about 11 degrees from its rotation axis. Jupiter tilts by about 10. Saturn, is almost perfectly aligned with its spin. The expected pattern is a magnetic field whose poles sit near the geographic poles, generated in a dynamo deep at the planet center, producing auroras concentrated at high latitudes where the magnetic field lines converge. Neptune breaks the pattern in two distinct ways. The magnetic axis is tilted about 47 degrees from the rotational axis, nearly halfway to the equator, and the magnetic field is offset from the planet's geometric center by roughly 55% of Neptune's radius. The dipole is displaced as well as tilted. The result is a highly asymmetric magnetosphere in which the strength of the field varies enormously across the planet's surface, and in which the magnetic poles sit not near the geographic poles, but at intermediate latitudes, in some sense roughly where southern South America would lie if it were placed on Neptune. This geometry has a clear physical origin, though it took decades of modeling to make it convincing. The dynamo that generates Neptune's magnetic field is not believed to operate close to the planet center in the way that the dynamos of Earth and Jupiter do. It is believed to operate in the ionic water layer of Neptune, ice mantle, at intermediate depths between the rocky core and the outer atmosphere. At those depths, the extreme pressures and temperatures dissociate water molecules into freely moving hydrogen and oxygen ions, producing an electrically conducting fluid that can generate a magnetic field through its slow churning motion. Generating a magnetic field in an off-center shell, rather than at the very core, naturally produces a tilted, offset, asymmetric dipole. The geometry that Voyager 2 measured, and that later observations have refined, is a direct consequence of where inside Neptune the dynamo lives. The same exotic phase of matter that helps explain Neptune, heat retention, also explains why its magnetic field is shaped the way it is. The strange tilt is not an accident. It is a signature of an unusual interior. The auroras that this field should produce eluded telescopes for 30 years. The Voyager 2 flyby detected the strong magnetic field. Models predicted that Neptune's magnetosphere should funnel charged particles from the solar wind into the upper atmosphere along the field lines, producing auroral emissions that ought to be visible at infrared wavelengths. On Jupiter, Saturn, and Uranus, the trihydrogen cation, a positively charged molecule made of 3 hydrogen atoms, had already been detected through its infrared emission lines. On Neptune, the same molecule was predicted but consistently failed to appear in any observation. Ground-based searches, using the Keck Observatory and the NASA Infrared Telescope Facility and other large instruments, found nothing. The non-detection was puzzling. The magnetic field was clearly strong. The solar wind clearly reached the planet. The geometry of the magnetosphere clearly funneled particles toward the magnetic poles. Yet the auroras refused to show themselves to any instrument the modern era of astronomy had built. For 30 years, Neptune was the only giant planet whose auroras remained, in the infrared, entirely absent from the record. The breakthrough came from the James Webb Space Telescope. Using its near-infrared spectrograph at extraordinary sensitivity, the telescope detected the trihydrogen cation in Neptune's upper atmosphere for the first time in observations made during its early science runs. The infrared images showed auroral emission appearing not as polar caps in the way that auroras appear on the Earth and on the other giant planets, but as bright patches in the southern mid-latitudes of Neptune. The location was, in fact, exactly where the tilted offset magnetic field would have predicted, once the geometry was properly accounted for. Neptune's auroras glow at mid-latitudes, not at the poles, and they had been there the whole time, waiting for an instrument sensitive enough to see them. The auroras themselves are visually striking when rendered from the infrared data. They appear as faint glowing regions on the planet, southern hemisphere, well away from the geographic pole, marking the places where the magnetic field lines connect down into the upper atmosphere from above. They tell us that Neptune is not isolated from the solar wind. Charged particles from the Sun, however faint that wind is at 4.5 billion kilometers, still reach the planet, still slide along its tilted magnetic field lines, and still deposit energy into the upper atmosphere at the points where the field lines meet it. The Sun, in this sense, is not entirely absent from Neptune as atmospheric story. It plays a small but visible role in the upper layers, even as the deep wind structure runs on internal heat. The James Webb observations contained an additional surprise, which deepened the mystery of Neptune's upper atmosphere. The telescope was able to measure the temperature of Neptune's ionosphere, the layer of atmosphere where ultraviolet light strips electrons from atoms and produces a plasma of charged particles. The Voyager 2 measurements, decades earlier, had established a baseline ionospheric temperature of roughly 700 Kelvin. The recent James Webb measurements indicated a temperature of roughly 358 Kelvin, just over half the Voyager value. Neptune's upper atmosphere had cooled by several hundred degrees over a few decades. This cooling was consistent with an independent set of ground-based studies, which had documented a similar dramatic cooling in Neptune's stratosphere using 20 years of thermal infrared observations. Taken together, the results suggest that Neptune's upper atmosphere is far more variable than anyone had expected. The planet receives almost no warmth from the Sun, and yet its upper atmospheric layers have been swinging in temperature by hundreds of degrees over a few decades. The cooling also helped explain why the auroras had been so hard to find. A hotter ionosphere produces stronger trihydrogen cation emission. As the ionosphere cooled, the emission dimmed. By the time astronomers had been searching for it for 2 or 3 decades, the auroras had likely fallen below the detection threshold of every instrument that was not the most sensitive infrared space telescope ever built. This particular detail is, in its quiet way, one of the more humbling pieces of the Neptune story. The auroras had been there all along. The instruments that searched for them had not been wrong about the physics. The brightness of the emission had simply been lower than the searchers assumed, because the temperature of the atmosphere that produced them had quietly dropped over time. For 30 years, Neptune's sky was not as bright as predicted, and only the patient continuing improvement of telescope technology was able to confirm what had been changing. The auroras, the cooling, and the strange magnetic geometry together speak of an upper atmosphere that is genuinely dynamic. It is not a passive blanket on top of the wind layer below. It interacts with the solar wind from above, with the magnetic field generated below it, and with the slow chemistry of methane photolysis that produces the seeds of the deeper clouds. It changes its temperature on timescales of decades. It changes its visible cloud population on timescales of a few years. It changes its brightness in the infrared on timescales of a single 11-year solar cycle. Almost nothing about Neptune, upper atmosphere, is static. Almost everything in it is in slow, ongoing transition, even as the deeper wind layer holds its planet-wide jets in place. The picture, taken in full, is one of a world that is dynamic at every level you can examine. The visible clouds breathe in and out with the sun. The dark vortices come and go on the rhythm of a few years. The wind layer runs continuously on internal heat. The magnetic field tilts in a way that puts the auroras in unfamiliar places. The upper atmosphere quietly cools or warms across decades. Below all of this lies the dense ice mantle, with its superionic phases and its diamond rain, and at the very center the small rocky core, glowing at temperatures comparable to the surface of the sun. None of these layers are still. None of them are simple. The blue exterior of the planet is, in some sense, the calm face of a world that is, at every depth, doing something. Part 9. The crushing furnace beneath. Almost everything inside Neptune has been inferred rather than observed. There has never been an atmospheric probe sent to the planet. There has never been a deep instrument package dropped into its clouds. The interior is known only through the laws of physics, the behavior of the gravitational field as Voyager 2 flew past, and the results of laboratory experiments here on Earth that try to reproduce the relevant pressures and temperatures in compressed targets, in laser-driven shock chambers, and in diamond anvil cells. The picture that has emerged is consistent, well-constrained in broad strokes, and, in detail, deeply strange. The visible cloud tops of Neptune are the warm boundary of the planet, even though they hover near -214 degrees Celsius. Above them lies a thin upper atmosphere, then the much thinner ionosphere, where the auroras live, and then the boundary with interplanetary space. Below the visible cloud tops, the pressure rises rapidly with depth. Within a few hundred kilometers downward, the pressure passes from one Earth atmosphere to several tens of Earth atmospheres. Within a few thousand kilometers, it has crossed into the regime where ordinary intuitions about atmospheres begin to fail. The first transition happens at the boundary between the hydrogen-helium envelope and the so-called ice mantle. The envelope, dominated by molecular hydrogen with a small fraction of helium and traces of methane and other compounds, gradually gives way as depth increases. Hydrogen, under sufficient pressure, transitions from a molecular gas to a denser fluid phase. Below this, the mantle proper begins, dominated by water, methane, and ammonia in compressed forms. The word ice, in the term ice giant, is misleading. At the temperatures and pressures of Neptune's mantle, these substances are not the familiar crystalline frozen solids you would find on the surface of a moon. Some of them are dense, superheated fluids. Some of them are mixtures of ions and free electrons. Some of them are in phases that have no obvious counterpart in everyday matter. The mantle is hot, opaque, and chemically active. It is, in a real sense, a separate world embedded inside Neptune, with rules of its own. Within the mantle, water undergoes some of the strangest transitions known to planetary science. Laboratory experiments and theoretical calculations both predict that water, under pressures of several hundred gigapascals and temperatures of several thousand Kelvin, enters a phase called superionic water. In this phase, the oxygen atoms lock themselves into a rigid crystalline lattice. The hydrogen atoms, much smaller, detach from their parent molecules and flow freely through the lattice as bare protons. The substance is simultaneously a solid with respect to the oxygen and a liquid with respect to the hydrogen. It is a phase of matter that has no everyday equivalent. Solid and fluid in the same place, at the same time, in different aspects. Superionic water conducts electricity through the motion of its hydrogen ions and is the best current candidate for the electrically conducting fluid that generates Neptune's tilted offset magnetic field. The conditions are right. The location is right. The conductivity is right. The geometry of the resulting field would naturally be tilted and offset in the way that observation has shown. This is the bridge between Neptune's strange interior and its strange exterior. The same exotic phase of matter that holds the planet, heat, inside, is also what tilts its magnetic field outside. Methane, in the same conditions, behaves differently and equally strangely. Under pressures of a few tens of gigapascals, methane molecules break apart. The carbon atoms are squeezed out of their bonds with hydrogen. Free carbon, dense and resistant to further compression, organizes itself into crystalline diamond. Free hydrogen, lighter and more mobile, rises upward through the surrounding fluid. The result, slowly and continuously, is a precipitation of solid diamond crystals through the deep ice mantle of the planet. Diamond rain, in the casual phrase that has come to describe it. The diamonds fall, in a sense, but they do not fall through anything you would call a sky. They sink through a dense, hot, electrically conducting fluid mantle at depths where the pressures exceed any conditions a human technology has ever sustained for more than fractions of a second. As they sink, they convert gravitational potential energy into heat. They contribute, slowly and continuously, to the planet's internal heat budget. The amount they contribute is not precisely known, but the process is well grounded in the physics of carbon under pressure and in the laboratory experiments that have reproduced the relevant transitions. There is something quietly beautiful about this. The planet, deep inside, is making and unmaking diamonds, slowly, continuously, for billions of years. Some fraction of the heat that drives the wind speeds at the top is, in a sense, gravitational energy released by sinking diamond crystals, far below any altitude that any cloud could reach. The atmosphere at the top is being driven, in part, by the most ornamental substance the planet manages to produce, deep beneath any place a human eye could ever go. Below the ice mantle sits the rocky core. The core is small, by the standards of the planet as a whole. Best estimates place it at perhaps 1 to 1.5 Earth masses. It is composed of compressed silicates and metals, broadly similar in character to the bulk composition of the inner rocky planets, but under enormously different conditions. The pressures at the core boundary are estimated at several hundred gigapascals, more than 7 million times the Earth's surface pressure. The temperatures are estimated at perhaps 5,000 degrees Celsius, comparable to the surface of the Sun. This core is not a frozen dead lump at the bottom of a cold planet. It is a small hot furnace embedded in the center of the world, radiating energy outward through the surrounding mantle. Whatever residual heat it carries from formation, whatever heat it gains from ongoing gravitational settling, whatever heat it gains from chemical processes deep inside, it has been releasing slowly and continuously for 4.5 billion years. The energy that drives the winds at the cloud tops, on this view, has been climbing upward from the center of the planet for the entire time the planet has existed. The path that energy travels is also worth a moment, as attention. The core radiates and conducts heat into the surrounding mantle. The mantle, with its superionic phases and its diamond rain and its slow churning convection, carries that heat upward toward the boundary with the hydrogen-helium envelope. At the boundary, the heat enters the envelope and continues upward through a series of slowly convecting layers until it reaches the bottom of the wind layer at the cloud tops. There, the same energy that started at the core 5,000 kilometers deep below ends as kinetic motion in a thin shell of cold gas. 5,000 kilometers of layered exotic matter, each layer with its own rules, all of it cooperating to deliver fractions of a watt per square meter to the base of the atmosphere. You can sit with that picture for a moment if you like. A small rocky core at the center of a planet 4.5 billion kilometers away from the Sun, radiating energy outward. The energy crosses through a mantle of substances that do not exist on the Earth in any everyday form. It crosses through a shell of an exotic phase of matter that is solid and liquid at once. It crosses through layers in which diamonds form and sink. It crosses through a hydrogen-helium envelope. It arrives, at last, at a shell of cold gas at the very top, and there it becomes wind. And the wind, in turn, is what telescopes see from billions of kilometers away as the visible face of Neptune. The entire visible behavior of the planet, on this view, is the surface expression of a very long, very slow, very deep chain of energy transport that has been running quietly since the planet was young. Nothing about this chain is loud. Nothing about it is sudden. Almost none of it has ever been directly observed. The structure that planetary science has assembled, from gravity field measurements, from infrared thermal data, from laboratory experiments at extreme pressure, and from the slow accumulation of theory, is a description of a planet whose interior is unfamiliar, whose mechanisms are exotic, and whose visible violence at the top is the soft signal of an enormous and patient interior architecture below. Part X, Neptune, Moons and Rings, in brief, a short, quiet interlude before the closing sections. The video is about Neptune itself, but the planet does not exist alone. It carries a small family of moons, a faint and unusual ring system, and a complex history of interactions with these companions that in some ways is more dramatic than anything happening in the planet atmosphere. The tour here is brief by design. The point is not to catalogue everything in the system. The point is to let the listener feel that Neptune has neighbors and to fold those neighbors softly into the larger picture. The largest of the moons is Triton. It has a diameter of about 2,700 kilometers, which makes it one of the larger moons in the entire solar system, comparable in scale to our own moon. It orbits Neptune at a distance of roughly 350,000 kilometers. Its size is large enough to give it a roughly spherical shape, and its surface has been imaged at sufficient detail by Voyager 2 to reveal a remarkable landscape. Triton is unusual in almost every way that a moon can be unusual. It orbits Neptune in a retrograde direction, opposite to the direction in which Neptune itself rotates. It is the only large moon in the solar system to do so. Among the smaller captured moons of the outer planets, retrograde orbits are common. Among the large, geologically active moons of the giant planets, Triton is alone in moving in the wrong direction. This is one of the strongest pieces of evidence that Triton did not form alongside Neptune at the time the planet itself was assembling. Instead, it appears to have been captured by Neptune later, probably from the Kuiper Belt, where many similar icy bodies still exist. The capture is thought to have been a violent and complex event, involving the disruption of Triton, its original binary partner, and a long period of tidal interaction that gradually shaped the Moon's present orbit. Triton, surface is cold. Its temperature averages near -235 degrees Celsius, among the coldest known temperatures on any solid surface in the solar system. Despite this, Triton is geologically active. Voyager 2 observed plumes of nitrogen gas rising from its surface, reaching altitudes of perhaps 8 kilometers before falling back as nitrogen frost. These cryogenic geysers, as they are sometimes called, are thought to be driven by the heating of subsurface nitrogen ice by sunlight that filters through the Moon's thin, transparent surface. The heat causes nitrogen gas to build up beneath the surface until it bursts upward in narrow jets that travel along the wind direction in Triton, his extremely thin atmosphere. Beneath the surface, Triton may host a subsurface ocean of liquid water, kept warm by a combination of residual heat from formation, ongoing radioactive decay, and tidal interaction with Neptune. If the ocean exists, it would be small and difficult to access, but it would represent another body in the outer solar system where liquid water survives in the dark, far from the sun, beneath an icy crust. Triton would join a small group of worlds, including Europa around Jupiter and Enceladus around Saturn, where the standard expectation of the outer solar system as a frozen desert is contradicted by quiet, sustained, internal warmth. Triton's retrograde orbit, however, carries a long-term consequence. Over hundreds of millions of years, tidal interactions with Neptune are slowly drawing Triton closer to the planet. The orbit is decaying. At some point, perhaps 3.5 billion years from now, Triton will pass close enough to Neptune that the planet's gravity will tear it apart. The Moon will fragment into a vast cloud of icy debris, which will then settle into a brilliant ring system surrounding Neptune. For a brief astronomical interval after the disruption, Neptune may carry rings as spectacular as the ones Saturn carries today. The rings will eventually dissipate, but for a long span of time, the planet will be visibly transformed. It is, in its way, a quietly hopeful image. The Moon and the planet are tied to one another by gravity. The tie is gradually drawing them closer. The eventual end of one will be the beginning of a new and beautiful ornament for the other. None of this will happen on a timescale that has any meaning for human life. But the planet and its moon are, in some sense, already arranged for the slow, patient transformation, and have been arranged for it since the moon was first captured. Beyond Triton, Neptune carries at least 14 other confirmed moons. Most of them are small and irregularly shaped. They fall into two broad groups. The first group are the inner regular moons, which orbit close to Neptune in roughly circular, roughly equatorial paths. Naiad, Thalassa, Despina, Galatea, Larissa, and several others move close to Neptune, often in the same region as the planet's faint rings. These moons probably formed in something close to their current orbits, or were placed there by the same dynamical events that captured Triton. Galatea, in particular, plays a small but important role in the structure of the rings, as we will see in a moment. Proteus, somewhat larger than the others at about 420 kilometers across, is the largest of the inner regular moons. It is dark, irregularly shaped, and difficult to observe, but it is, in mass, second only to Triton. The second group are the outer, irregular moons, captured into wide, tilted orbits long after Neptune formed. These are smaller still, and their orbits are often inclined and elongated, signs that they were captured rather than formed in place. Nereid is one of the better known. It moves around Neptune in a highly eccentric orbit that ranges from about 1.5 million to 9.5 million kilometers in distance across a single circuit. Some of the outer irregular moons orbit in retrograde directions, some in prograde directions. They are reminders that Neptune, like every giant planet, has been collecting passing objects throughout its long history. The ring system of Neptune is faint, dusty, and unusual. There are at least 5 known rings, all of them dark, all of them composed of fine particles of carbon-rich dust. They are difficult to see from the Earth and were not confirmed until Voyager 2 imaged them up close. The most striking of the rings is the outermost, called the Adam's ring. The Adam's ring is unusual in that, instead of being a smooth, continuous loop of material, it contains 5 distinct concentrated clumps of material. These clumps, called ring arcs, sit in well-defined positions around the ring. By the simple physics of orbital motion, the arcs ought to spread out and dissolve into a smooth loop within a few orbits. They do not. They have persisted in roughly their observed positions for as long as we have been able to track them. The mechanism that holds the arcs in place is thought to involve gravitational interactions with the small inner moon Galatea, which orbits just inside the Adam's ring. Galatea's gravity creates resonances that confine the dust into discrete groups, holding them against the natural tendency to spread. The full details are still under study. Like much of Neptune's system, the arcs are a feature that has been described carefully from a great distance, but has not been studied closely with a dedicated mission. The exact dynamics may yet be more complex than current models account for. The rings as a whole are unlikely to be ancient. Like many ring systems in the solar system, they are probably the debris of smaller bodies that broke apart, perhaps in collisions with passing objects, or under the tidal stresses of orbiting too close to the planet. Over time, the dust slowly spirals inward and is lost, either by colliding with Neptune, atmosphere, or by being swept up by inner moons. New ring material is presumably supplied as further small impacts and disruptions occur. The system is in slow turnover, in the way that all dusty ring systems seem to be. Holding the moons and rings in mind alongside the planet itself makes for a quiet picture of Neptune's neighborhood. The planet at the center, 4.5 billion kilometers from the Sun, with its violent atmosphere and its tilted magnetic field and its exotic interior. Triton turning quietly in the wrong direction around it, with its nitrogen plumes and its possible subsurface ocean and its slow descent into a future ring system. A small family of dim moons orbiting between them. Faint, dusty rings, with their persistent arcs held in place by small shepherding moons. None of it is bright. None of it is loud. All of it is moving, slowly, patiently, exactly as it has been moving for billions of years. Part 11, where Neptune stands among the giants, a consolidating section in which we set Neptune beside its 3 sibling giants in turn and let the inversions settle. Each comparison is brief on its own. The cumulative weight is what matters. By the end of the section, the listener should feel that the conventional gradient of the solar system, in which distance from the Sun is supposed to predict atmospheric calm, has been broken not by chance, but by the architecture of the giants themselves. The first comparison is Jupiter. Jupiter is the largest planet in the solar system. Its mass is more than 317 Earths. Its volume could contain over 1,300 Earths. It sits at about 5 times the Earth, distance from the Sun, and receives about 4% of the Earth solar input per square meter. It is the closest of the giants to the Sun, the most massive of them, and the most spectacularly weather-driven of them in the eye of the casual observer. The Great Red Spot, a stable storm wider than the Earth, has been observed for at least several centuries. The atmosphere is organized into dozens of alternating cloud bands, each with its own characteristic color and wind direction. Lightning lights up the deep cloud layers. Auroras burn at the poles. The planet is, in nearly every visible respect, the archetype of atmospheric violence. By any naive accounting, Jupiter should hold every record. It has more mass, more solar energy, more internal heat in absolute terms, and more atmospheric depth than any other planet. And yet Jupiter does not hold the wind speed record. Its sustained wind speeds peak at perhaps 400 to 500 miles per hour. Powerful by any standard, but not the most powerful. The most powerful are at Neptune, a planet roughly 1/20th Jupiter's mass, 6 times farther from the Sun, with an internal heat flux that, in absolute terms, is far smaller than Jupiter, c. The largest planet in the solar system does not win the wind contest. The smallest of the giants does. This single comparison, on its own, is enough to break the simple intuition that bigger and warmer means windier. The second comparison is Saturn. Saturn is the second largest planet, with a mass of about 95 Earths and a volume of about 764 Earths. It sits at about 10 times the Earth's distance and receives roughly 1% of the Earth's solar input per square meter. Its rings are the most beautiful in the solar system and have been studied at close range for years by a long-duration orbiter. Its atmosphere is less aggressively banded than Jupiter's, but it has its own striking features. The hexagonal jet stream at the North Pole, the episodic great white spot storms that erupt roughly once per Saturnian year, the long bright cap at each pole, the subtle modulation of cloud structure across the disk. Saturn also has a substantial internal heat source. It radiates about 1 8/10 of what it absorbs from the Sun, slightly more in proportion than Jupiter. Its peak sustained winds are higher than Jupiter, reaching about 1,100 miles per hour at the equator. But, again, they do not exceed Neptune's. Saturn is closer to the Sun, larger, internally hotter in absolute terms, and yet at the cloud tops, it moves more slowly than the small distant ice giant at the far edge of the planetary system. The wind speed record continues to belong to the planet that, by every intuition the inner solar system would supply, should hold it least. The third comparison is Uranus. This is the cleanest test. Uranus is roughly the same mass as Neptune, with about 14.5 Earth masses to Neptune, 17. Their compositions are similar in broad strokes, with a small rocky core, a thick mantle of compressed water and methane and ammonia, and an outer envelope of hydrogen and helium. Their distances from the Sun differ by a factor of about 1.5, with Uranus at roughly 20 times the Earth distance, and Neptune at roughly 30. The solar energy budgets, while different in absolute terms, are both very small compared to the energy budgets of the inner planets. What separates them is internal heat. Uranus radiates almost no excess heat. Its energy balance ratio is close to 1, essentially in thermal equilibrium with the Sun. Neptune's ratio is about 2 6/10. The two planets are siblings in mass and composition. They are dramatically different in their internal energy budgets, and the atmospheric consequences are correspondingly dramatic. Uranus, as Voyager 2 found it in the mid-1980s, showed a nearly featureless pale blue-green disk with almost no visible cloud structure. Its winds, though present, are modest by giant planet standards. Its weather, in general, is muted. Neptune, the near-twin, is the most violently active atmosphere among the giants. The Uranus-Neptune pair is, in some sense, the cleanest experiment the solar system has run on the question of what powers giant planet weather. Two planets of similar mass, similar composition, and similar large distance from the Sun, with dramatically different internal energy budgets, producing dramatically different atmospheric behavior. Where the internal engine is large, the atmosphere is violent. Where the internal engine is small, the atmosphere is calm. The Sun, in both cases, is a spectator. The internal heat, in both cases, is the variable that matters. What this pair reveals is that the conventional gradient of the solar system, in which solar energy decreases outward and atmospheric activity supposedly decreases with it, was always a partial picture. The gradient is real for the inner planets, where solar input does dominate the energy budget. The gradient breaks down completely for the outer giants, where internal heat can overwhelm the solar contribution by factors of 2 or more. Neptune is not an anomaly. Neptune is what an ice giant with an active internal engine looks like. Uranus is what an ice giant without one looks like. The fact that they are otherwise so similar is what makes the comparison so clean. This insight reaches beyond Neptune. The thousands of planets that we have discovered around other stars are not arranged according to the simple inner to outer gradient that our textbooks once suggested. Some of them are very close to their host stars, with atmospheres blasted by intense radiation. Some are very far out, with stellar input that is, by our standards, vanishingly small. By the simple gradient, the distant ones should be quiet. By Neptune's lesson, they may not be. A planet at Neptune, mass, in an outer orbit around its host star, could still possess a vigorous internal heat source. It could still have a shallow, low-friction atmosphere. It could still be capable of generating extreme winds in the dark, far from any stellar warmth. We have not yet been able to measure exoplanet atmospheres at that level of detail. When we can, Neptune has already warned us that some of them will surprise us. There is a quieter way to hold this. The solar system is not arranged into a tidy ladder of intensity, from hot inner planets to cold outer ones. It is arranged into a small set of very different worlds, each one shaped by the particular combination of its mass, its composition, its formation history, and the energy it carries inside. Neptune is the outermost. Neptune is the smallest of the giants. Neptune is the coldest of the giants by the calmest measurements. And by the measurements that count for wind, for storm, for vortex, for atmospheric variability, for sheer kinetic activity at the cloud tops, Neptune is, against every expectation, the most physically active. The far edge of the planetary system is not the quiet endpoint. It is, in this one important respect, the loudest place we have. Part 12. The thinness of what we know. There is something worth holding gently at the heart of the Neptune story. Almost everything we know about the planet has been pieced together from a single brief visit more than 35 years ago, and from decades of patient, distant looking, with telescopes that were not designed for Neptune in particular. The planet has been studied, in the strict sense, by exactly one spacecraft for a few hours in the late summer at the very end of the 1980s. Nothing has been close since. Nothing has dropped into its clouds. Nothing has measured its winds at depth. Nothing has touched its mantle. Nothing has tasted its chemistry up close. It is worth pausing on this, not as a complaint, but as a quiet observation. For comparison, Jupiter has been studied by 6 dedicated spacecraft, including an orbiter that spent about 8 years in residence, and another that is still operating today. Saturn was studied for roughly 13 years by the Cassini orbiter, long enough to watch its seasons change, to fly past every major moon up close, and to dive between the rings before finally being directed into the planet itself at the end of the mission. Mars has been visited dozens of times, by orbiters and landers and rovers across several decades. Venus has been visited and revisited. Mercury has been mapped. The Moon, of course, has been walked on. Neptune has been visited by one spacecraft, once. Voyager 2 was not specifically designed to study Neptune. It was designed for the entire grand tour of the outer solar system, with instruments built in the 1970s, calibrated for a wide range of possible environments, and pressed into service at Neptune as part of a survey that was nearing the end of its primary mission. The spacecraft saw roughly half the planet in sharp detail. It measured wind speeds at a limited number of latitudes. It detected the dark spots, the bright scooter, the methane companion clouds, the auroral signatures, the rings, the moons. It spent a few hours in the system, then continued outward forever. Everything else has been done from at least 4 billion kilometers away. The Hubble Space Telescope has tracked the dark spots over decades, watched the clouds come and go, observed the changes in the planet as appearance through multiple solar cycles. The James Webb Space Telescope has, in recent years, detected the auroras and measured the cooling of the upper atmosphere. The Keck and Lick and various other ground-based observatories have contributed their own long-term records. The Very Large Telescope in Chile recently detected a Neptunian dark spot from the ground for the first time in history. All of these instruments have done extraordinary work. None of them substitute for what a dedicated mission could provide. What such a mission could provide is enormous. An orbiter, circling Neptune for years rather than racing past in hours, could watch the dark spots from formation through migration, oscillation, reversal, fragmentation, and dissipation in real time. It could trace the storm life cycle beat by beat, instead of catching snapshots months apart and inferring the dynamics between them. It could measure wind speeds at every latitude and altitude, building a three-dimensional map of the atmospheric circulation that Voyager 2 could only sketch in 2 dimensions from one vantage point on a few hours of close approach. It could map the gravitational field of the planet in fine detail, revealing how the deep interior is structured. It could track the magnetic field over months and years and watch how the dynamo deep in the ice mantle expresses itself in time. An atmospheric entry probe, if it were included in such a mission, would do something no instrument has ever done. It would descend through Neptune's atmosphere, measuring temperature and pressure and composition and wind speed at the moment of its passage, sending data back to the orbiter as it fell deeper and deeper until pressure or temperature destroyed the instrument. Such a probe would directly answer some of the most basic questions that 35 years of remote observation have left open. What is the chemistry of the atmosphere below the cloud tops, in the layers where the dark spots actually live? What are the wind speeds at depth, where remote observation cannot reach? How smoothly does the atmosphere transition from hydrogen and helium to the dense ice mantle below? How efficiently is heat carried upward from the interior to the cloud tops? Each of these questions has had useful theoretical answers for decades. None of them has had a direct measurement. There are concepts for such missions. There have been proposals. Studies have been completed. The relevant agencies have, at various points, ranked an ice giant orbiter among the highest priorities for the next generation of planetary missions. Even under optimistic timelines, however, a Neptune orbiter would not arrive at the planet until perhaps the 2040s or 2050s, more than 50 years after Voyager 2's flyby. Building, launching, and flying a spacecraft to the outer solar system is, in the gentlest possible sense, a slow undertaking. The launch alone is a decade-long preparation. The cruise is another decade or more. The mission itself is years. The total time, from formal start of work to the first close-up images, will be measured in generations of working scientists. For now, the Neptune we know is a planet glimpsed through fragmentary observation spread across 35 years. The dark spots have been tracked intermittently. The wind profiles have been measured at a limited set of latitudes. The internal structure has been inferred from remote data, theoretical modeling, and laboratory experiments performed on Earth at extreme pressures. The atmospheric composition below the visible cloud tops remains almost entirely unknown. The exotic phases of water and methane and ammonia in the deep ice mantle, the precise mechanism that generates the tilted offset magnetic field, the detailed vertical structure of the dark vortex storms, the chemistry of the deep atmosphere at pressures millions of times greater than the Earth, surface pressure. All of this remains, in the cleanest possible sense, unobserved territory. We have inferences. We do not have measurements. The result is that the violence the video has been describing is almost certainly incomplete. There are storms we have not seen because no telescope was looking at the right time. There are wind features at latitudes Voyager could not measure. There are atmospheric processes occurring beneath the cloud deck that no instrument has ever detected. There may be lightning we have not yet observed. There may be chemistry we have not yet recognized. The James Webb aurora detection was a vivid reminder of this. For 30 years, scientists searched for the trihydrogen cation in Neptune's atmosphere and found nothing. The auroras had been there the whole time, dimmed by a slow cooling of the upper atmosphere that no one had predicted. When the right instrument finally looked with sufficient sensitivity, the signal was unmistakable. How many other Neptunian phenomena are hiding in the same way, waiting for the right instrument and the right wavelength and the right patient observation? The honest scientific assessment is that Neptune holds more open questions than any other major planet in the solar system. Not because Neptune is intrinsically more mysterious than the others, but because we have invested less observational effort in understanding it than we have in understanding any other giant planet. The ratio of atmospheric complexity to observational coverage is the largest in the planetary family. We know enough to recognize that Neptune is extraordinary. We do not know enough to explain why, in any complete way. There are particular open questions that are worth naming in the calm register this section calls for. What, precisely, supplies the excess internal heat that drives Neptune's atmosphere? Is it primarily the residual heat from formation, or is gravitational settling actively contributing? Or is the slow chemistry of diamond rain releasing energy at the rate that the picture seems to need? Why does Uranus, so similar in mass and composition, radiate so much less of its own heat? Is its interior fundamentally different, or is the heat there but blocked from escaping by a layer that prevents convection? What is the detailed three-dimensional structure of the dark vortex storms? What altitudes do they occupy? What are the wind profiles inside them? What chemistry separates the dark interior from the bright methane ice companion clouds at the edges? Why do they appear in different hemispheres, drift to different latitudes, and end on a rhythm of a few years? What is the exact configuration of the ionic water dynamo inside Neptune, ice mantle? How does the strange tilt and offset of the magnetic field evolve over time? And how, if at all, does the dynamo respond to the slow rearrangement of the interior over geological time? Does the magnetic field strength change on timescales we could observe with a long-duration mission? How does the atmospheric circulation connect to the deep interior across the boundary between the thin wind layer and the dense mantle? What signals from the interior, if any, can be read in the visible cloud structure? What signals from the wind structure, if any, can be read in the gravitational field, the magnetic field, the infrared emission spectrum? Why has the upper atmosphere been quietly cooling over recent decades? Is the cooling part of a longer cycle, or is it a one-way trend? Has the atmosphere passed through similar cooling and warming episodes in the past, on timescales too long for the modern observational record to capture? How representative is Neptune of cold Neptune mass exoplanets in outer orbits around other stars? Are most such planets similarly active, or is Neptune unusually energetic for its class? Without a closer look at any of these worlds, all of these questions remain open in essentially the same way. The list of open questions is long. It is, in some sense, longer than the list of confirmed answers. And that is, in the calm register of this video, not a frustration, but a quiet feature of the situation. Every long-running scientific question is a door that the universe has left open. Neptune carries more such doors than any other major planet. The mission that finally walks through some of them is, almost certainly, decades away. Until then, the planet remains exactly what it has been for the entire span of human observation. A bright blue point in a long telescope. A field of cloud structure in slow change. A magnetic field tilting in the dark. An engine running quietly inside, supplying the energy for the most violently active atmosphere among the giants by mechanisms that have been described carefully but not yet directly measured. Part 13. Closing reframe. The word was not the right one. The title used the word brutal. It is a useful word for a title. It pulls a glance. It promises something extreme. The video has, in its own way, paid the title off. The winds are real. The storms are real. The atmosphere is real. The internal engine is real. The numbers, measured carefully by the only spacecraft that has ever been close and by the patient telescopes that have looked across the dark since, all confirm that Neptune is the most physically active atmosphere among the 4 giant planets. The mystery in the title is honest. Now, in this last section, the word can be quietly set down. Brutal is the wrong word for what Neptune is doing. Brutal implies an act directed at something. A brutal storm is brutal toward a coastline. A brutal cold snap is brutal toward the people who must walk through it. Brutality is a property of the relationship between an action and a recipient. Neptune does not have a recipient. The planet sits 4.5 billion kilometers away. Nothing in its atmosphere reaches any human ear or skin. Nothing about its wind speeds threatens anything that has ever lived on the Earth. The most violent atmospheric flow we know of, on a planet smaller than the giants closer in and farther from the sun than any of them, blows endlessly across an empty sky. The mechanical violence of Neptune is, in this important way, a feature of the planet alone. It is not a feature of any relationship between Neptune and anything else. There is no continent against which the winds break. There is no ocean to be churned. There is no city to be flattened. There is no creature to be lifted, frozen, displaced, or harmed. The atmosphere moves at supersonic speeds across a planet whose entire surface is gas. The dark spots form, drift, oscillate, reverse, and fade across a face that no one is watching except a few distant telescopes for a few minutes a year. The diamond rain inside falls in pressures no living thing could survive, even for the smallest fraction of a moment. None of it has a target. This is one of the quieter gifts of cosmic distance, when you let yourself sit with it. The activity is real. The energy is real. The numbers are real. And yet none of it is aimed at you. Neptune is enormous, distant, indifferent, and mechanical. It is not malicious. It is not menacing. It is not engaged with you in any way at all. It is simply doing what it does, has been doing for billions of years, and will keep doing for billions of years more. The video has been an extended description of a system that is, in the most ordinary possible sense, just running. There is a way to hold this that has been useful for many of the videos that have come before. The most beautiful events in the galaxy happen in absolute silence because the gas between objects is too thin to carry a sound. A supernova in the next galaxy over makes no noise that any ear could hear, even one positioned next to it, because no atmosphere connects the explosion to the listener. The same is true of Neptune in a smaller way. The winds at the cloud tops are racing at more than 1,300 miles per hour. Standing alongside them in a hypothetical body that could not be harmed, you would feel them as a steady, smooth, planet-wide flow of frigid gas. They would make a sound in the thin atmosphere of Neptune itself, somewhere in the dense lower layers. They would make no sound at all in the vacuum between Neptune and the Earth. The violence travels nowhere. The energy stays where it is. The atmosphere holds onto it for the long centuries during which the engine inside continues to supply it. Many of the wonders we describe in these videos are quiet at the source. Galaxies turn slowly, in silence. Black holes hold their event horizons in silence. Even nebulae, expanding for tens of thousands of years across light years of space, pass through their long lives without a sound. Neptune is the opposite of all of them. It is physically loud at the source, in the strict sense that it is the most kinetically active atmosphere we know of in the planetary system. It is silent on arrival because the kinetic energy goes nowhere, never reaches us, and never could. There is something almost restful in that pairing. A planet doing one of the most extreme things in the family, and the extremity is sealed inside the planet itself. It is not a fact about your evening. It is not a fact about your day. It is a fact about a small blue point at the edge of the sun influence, holding its own weather quietly and entirely to itself. You can put the word brutal down beside the planet. You can leave it there. What stays after the word is set down is just the planet. A small blue sphere, 4 times wider than the Earth, at the far edge of the solar system. A faint, sharp sun in its sky, casting almost no warmth. An atmosphere of hydrogen and helium, with traces of methane, deep blue from the methane absorption. A wind layer racing endlessly around the planet, faster than any wind anywhere else. Dark vortices forming, drifting, fading. Mid-latitude clouds coming and going in slow rhythm with the distant sun. A tilted magnetic field, producing auroras in the wrong places. An ionic water mantle below, slowly churning, generating the field, holding the heat. A precipitation of diamond crystals through the deeper layers. A small rocky core, glowing at temperatures comparable to the sun, radiating energy outward. A handful of moons, with retrograde Triton at the largest scale, and a faint dusty ring system held in arcs by small shepherding companions. None of this needs anything from anyone. None of this is going to stop on the timescale of any human life. The mystery is honest. The fear is unnecessary. The brutality is mechanical and contained. The planet is one of the most beautiful objects in the night sky, and one of the least visited by any instrument we have built. It will continue, in its own quiet engine room, doing exactly what it has been doing for the entire history of the Earth, exactly what it will go on doing for at least as long as the sun continues to shine. There is nothing about it that you have to carry. There is nothing in any of it that you have to fix. It has been there. It will be there. The blue holds. The wind blows. The engine inside runs. And so we leave Neptune, where we have always left it, turning slowly in the long dark at the edge of the sun. Slight, its winds racing endlessly across an ocean of cold gas, indifferent to whether we are watching. The engine inside will keep turning. The dark spots will keep coming and going. The blue will hold across billions of years more. There is nothing in any of it that needs anything from you. Let your breathing slow. Let your shoulders settle. Let the sky behind your eyes grow quiet. Sleep well and good night.